So today we're going to talk about a phenomena called polarization. We're going to define what that phenomena is. You're going to use polarization to look at the three-dimensional characteristics of electromagnetic light, and we're going to apply a mathematical relationship to it called Malice's law. Okay, three things. Let's get started. Let's have a quick review of the electromagnetic spectrum. Remember, this is a group of waves of differing wavelength, but having the same speed, right? All traveling at 3 times 10 to the power of 8. And basically, there is a group, so from radio to microwaves to infrared, visible, ultraviolet, X-rays, and gamma. These are all examples of electromagnetic waves. Now, this is the kind of diagram that I've shown you before. Two-dimensional representation of the waves, where you can see the wavelength is evident, that it's like a flat diagram. What I'm going to show you now is a more realistic representation of what electromagnetic wave looks like. Electromagnetic waves are three-dimensional, right? It's like a cylinder of light traveling, and it has a horizontal and a vertical, a more accurate depiction, because electromagnetic waves are actually three-dimensional, right? And you can simplify it, so this would be a front view representation of an electromagnetic wave. It would be like a little cylinder traveling. Imagine this light wave traveling towards you right now. It would be like a cylinder. And what exactly is that cylinder? Well, it's actually electromagnetic waves consist of oscillating magnetic and electric fields. I'm throwing this in here now, but we haven't covered any of this, and it's not important that you don't have to concern yourself with that definition at this moment. But in terms of what we're doing now, what you can do is visualize this cylinder, right, as having a horizontal and a vertical component. That would be your magnetic and your electrical fields, right? So we can represent it this way. An electromagnetic wave then would be horizontal and vertical waves traveling together. Something like this. So that's what an electromagnetic wave looks like. Okay? And in terms of this phenomena, polarization, this would be an unpolarized light wave. That means nothing's happened to it. It's totally complete and it's fine. Most of the light sources that you use, natural light sources, are unpolarized light. So when we get light from the sun, I don't know what those letters have gone down there, but I'll fix that in a minute. The sun, a candle, a lamp, all of these radiation sources of light, they are giving off unpolarized light. That means that the visible light that's coming off them looks like this. It has horizontal and vertical components, right? Now, this polarization phenomena involves doing something to that three-dimensional electromagnetic wave. Now, firstly, I want you to think a little bit, what do we polarize? Well, polarizing materials are materials which are sometimes used for sunglasses. They're used on the screens of computers. So they're usually specially made materials which are designed to change the intensity of light, right? So that's something that will polarize. Reflective surfaces also polarize, but we'll talk about those in a moment. We're going to look at the phenomena of polarization, and for that we need to understand, well, what's doing the polarization. A polarizing filter, for example, let me introduce it here, is a plastic which is made from long molecules, right? These long molecules are formed in chains, and what they do is they kind of literally form these layers, which then will have a peculiar effect on the light. Okay, so a polarizing lens is designed to reduce intensity usually, or to change light on purpose. Sometimes we use them for photography as well. Here you can see a polarizing lens is changing this very glary very bright picture into something which is much prettier and has much better defined features. And that's all done by polarization. So polarization is done with a polarizing lens, which is a specially created material which is used to create special light effects. So what is polarization? Well, you take this three-dimensional light wave, and what you're doing is you're forcing it to go through a filter which only allows the light in one direction, right? So this is our unpolarized light. We put a filter in place here, and then what comes out of it is plain polarized light. That means it no longer has this three-dimensional property, okay? So this is one way of visualizing it. This is your unpolarized light, and your polarizing filter, right, forces only one direction through. And this is what we would call plain polarized light. What is the polarizing filter actually doing? Well, as I described before, the filter is designed to only allow the light one way. We can visualize it like this. We can visualize it as a filter which has lines or holes, right, in one direction. And those holes allow only the light that is in that direction through. Okay, so that's the polarization effect. That's when you polarize light. What we can do next is we can create a total blackout effect. Now this is when we polarize something twice. So starting with our unpolarized light, you use one filter in one direction, and what that causes is light of a single direction through, plain polarized light. So what you do now is you use a second filter, right? A second filter which has the plane of polarization, these gaps, at 90 degrees to the original one, right? So that now it's only going to allow through vibrations which are this way. But of course, in our plain polarized light, we have vibrations only in this direction. So what would you expect to see here? Well, you shouldn't be able to see anything, because now no light is actually allowed through. These filters have actual special names. The first filter, which is causing the polarization effect, is called a polarizer. And the second filter, which is basically blocking the light completely, is called the analyzer. And this no light transmitted effect happens when these two, the polarizer and the analyzer, are at 90 degrees to each other. So this is a demonstration. When they're parallel, light goes through. When you move it at 90 degrees, they block the light out. Okay, so that's the polarizing effect. If you've got some nice sunglasses at home, you could probably play around with a computer screen, your laptop screen, and some decent sunglasses. Try playing around with that. See if you get a similar effect. The one that I found, 90 degrees. If you have the polarizer and the analyzer in line, nothing happens. You turn that polarizer around 90 degrees and you get no light traveling through. Okay, that's the polarizing effect. Parallel, 90 degrees. Reflection also happens by reflection. What's going on there? Well, you start off with unpolarized light, and non-metallic surfaces will polarize. They will act like your polarizing lens. So when that unpolarized light hits non-metallic surfaces, the light reflecting off them is polarized. If you then wear some glasses which have polarizing filters in them, then that polarizing light will disappear. And what you end up doing is cutting out like huge quantities of the light that's flying around, and gives you a much clearer view. Okay, so polarization is the same on a surface. It's just that the first filter is actually a surface, right? That's what's causing the polarization. So here we have a photo which is polarized and unpolarized. So here we have light coming from water, which is reflected, and so therefore is polarized, right? Now, with Polaroid sunglasses, that means if you wear your second filter, then what you get is this lovely clear view, because all the light that's reflected has gone, right? It's basically removed the reflection, so you're getting a nice clear view of the water. You don't have like loads of light flying around. You've actually gotten rid of the distraction, and this is what it's like normally. Now, to really understand this picture, I think to understand this concept, you need to understand something called total internal reflection, etc. So I wouldn't worry too much about it. The reason why this is clearer, though, is because you've removed all the light that was reflecting on it. Think of it like that, and then we'll come back to this when we do total internal reflection. And as a little appendix as well, there's a lot of liquids that, or solutions more importantly, that actually polarize light as well. They're called optically active solutions, and they're more for like chemistry, biology side of science. But sugar solution, for example, will do the same as a polarizer. They will actually polarize light, and this is a demo we'll do when we get to school. Eventually, but there's a video on the presentation that you might want to watch if you're interested in this. Okay, so let's go do some maths then. Let's look at Malice's law, which is the third thing I wanted you to think about. Now, Malice's law gives you a relationship between the intensity of light coming in, right? Intensity is related to the power, the energy per unit, the energy per second per unit area. And we'll look at that in a minute, but let's have a think about what this means in terms of the filters. You have an intensity coming in. It goes through the first filter, and of course that some of that intensity is removed, right? Because you're left with only the energy in one direction, the light in one direction. And then it goes through the second filter. Now, Malice's law states that the intensity at the end, this final intensity, is equal to the initial intensity, which is I naught, right, times the angle between the first filter and the second filter, right? The angle between the two, the polarizer and the analyzer. So you need this angle, and then you square the cosine of that angle. Another way of looking at that relationship is to create a ratio between the intensity in terms of the original intensity, I naught. So I over I naught equals cosine squared of the angle between the two. So let's have a look at this first question. If vertically polarized light falls on a polarizing filter, analyzer, so that its transmission direction is at 30 degrees to the vertical, what percentage of light passes through the analyzer? By percentage of light, it's asking, what is I over I naught? So we would work that out as cosine 30 squared. So if you work out the cosine of 30 squared, that gives you 0.75, which will lead to a percentage of 75%. Or you can leave it as a ratio, 0.75. That's fine. Okay, try some questions today and check your answers.